Hello everybody, and welcome to the Hidden Truths, a place where we explore scenarios, histories, and truths hidden from the public view. Big thanks to Cirnosad for compiling this, and today we're going to learn about critical mass, timing circuits, and with them, we will combine what we learned in Physics 1 and 2 to learn how the ultimate weapon was created, the nuclear bomb. In the previous installments, we learned about conventional bomb design and the importance of casing, timing, and symmetry. As it were, this is even more important for nuclear bombs, but keep it in mind as well as the principle of fission as we move forward. Nuclear fission is a chain reaction, but it exhibits an interesting phenomenon. For each type of reaction, slow, fast neutrons, etc., there is a probability of reaction taking place. Call the total reaction rate area as the cross-section. Every atom/reactant pair has one. Just like the decay rate, lifetime of daughter particles, and time to fission, there is no physics model that predicts cross-sections. They must be measured experimentally, across all energies and relative velocities of incoming neutrons. Apparatuses used is outside of our current scope. As an aside, you'll note the renaissance and different cross-sections depending on whether you want fission or capture. This can be exploited, for example, to filter out neutrons from a neutron source that aren't of a certain energy. This is accurate cross-sections are secret governments. State secrets. Let's look at the fission cross-section of plutonium-239 and uranium-235. We can note some things. Uranium prefers slow thermal neutrons. Plutonium prefers neutrons of certain energies. Plutonium also has a higher fission probability than uranium. Its cross-section is just way larger. The cross-sections are still relatively small compared to the very high probability of a reaction in a chemical explosion. Neutrons can actually move some distance away from the fissile material without reacting. Each material also generates a different average number of neutrons. When the total number of neutrons escaping our fissile material, the pit, is equal to the fission event neutrons generated inside, we call this a critical mass. We are, in fact, more interested in a supercritical mass because it means generating exponentially more energy. In summary, each fissile material has a fission cross-section, and if shaped as a sphere, each material under normal atmospheric conditions has a certain critical mass requirement to undergo a sustained chain reaction. You need 5 times more uranium than plutonium. Great, so let's just get a critical mass going. Oh wait, that's not a very good idea, is it? Of course not. It'll produce a huge amount of radiation, or may even explode the moment it gets a neutron event. Not like a nuke, but enough to kill you, wound you, and sicken you. We concluded that it's more important to keep the fissile material as subcritical mass until we want to detonate the bomb. Also, just like chemical explosives, conservation of momentum will tend to want to blow the critical mass apart, stopping the reaction. We need a casing. The most primitive design takes the above experiment and puts it in a chamber. This is known as a gun-type assembly and was dropped on Hiroshima. It was inefficient, produced a lot of fallout, and most of the material didn't even undergo fission before it blew through the casing. As you can see, this is a massive cross-section of the little boy, each with its many parts. A far better design was the very first one detonated, the implosion type design. A subcritical mass and neutron source are surrounded by electronically detonated explosives. With precise timing, all charges detonate in the compression of the material into supercritical mass. The higher compression meant that the effective critical mass was lower than the required. In fact, Fat Man used 6.4 kilograms, not the 10 kilograms required at normal pressures as a result. The precision time deformation and strong casing, the bomb weighed 6 tons after all, caused the supercriticality itself. And as you can see, we got the cross section of the Fat Man. The casing assembly keeps the detonation focused on the fission material, generating a huge shockwave internally. Imploding, this creates a critical mass, which then more rapidly undergoes fission. Thus, this nuclear bomb is essentially an amplifier of a chemical explosion. Kaboom! It is important to note the presence of a uranium-238 casing around the plutonium. This acts as an inner casing, holding the supercritical mass together. It also provides it with fast neutrons and reflects the fission-generating neutrons back into it, creating a smaller critical mass. This is known as a tamper, and it is very important in nuclear weapon design. This neutron reflector demonstrates how efficiency can be increased using static materials in a clever manner. Note also merely a change in geometry caused this massive nuclear explosion to happen. What happens to the energy produced by the nuke? It depends on the surrounding material. In the air, the energy absorbed by the atmosphere. This strips them of electrons, creating plasma, and this extremely hot plasma expands, creating deadly shockwaves. It also produces thermal energy, which is basically heat, X-rays, same thing as heat but higher energy, and residual radiation in the form of short-lived isotopes, basically fallout. The latter is either desirable if you want to render an area uninhabitable, or undesirable if you want to keep the place still livable. Distinctive to nukes is the creation of a plasma, which is also centered on a point. You see, a chemical explosion can never do this. The energy produced can only ionize a small percentage of atoms. Most of what is generated is heat and a shockwave. As an aside, plasmas can carry charges. Another tell, everyone knows hot air rises due to buoyancy, but there is a limit as well. It will encounter more and more cold and lower pressure as the air rises. Due to extreme temperature involved, nuclear bombs will create mushroom clouds that rise rapidly and to a very tall height. They are also far less susceptible to wind, drift, and the smoke is generated mostly below the luminous parts, not mostly shown above as combustion particles. As shown, the cloud isn't just fascinating. We can in fact estimate the yield of a nuclear explosion by its height. There is another important distinction. Due to the creation of plasma, the explosion, depending on its height, through both the action of the shockwave and the plasma, will create a large crater and crack/pulverize the soil around ground zero. The site access is a must for assessment. Depending on the yield and either surface depth or elevation of the nuclear explosion, the soil can also remain hot for far longer than a conventional explosion, which only reaches 3,000 to 4,000 degrees Celsius in the very initial phase. Nukes reach tens of millions of degrees with ease. And that's it for Physics 03. The key takeaways: the nuclear bombs do not detonate on their own. They require precise timing of explosions. Critical mass is also not an intrinsic figure of a material, but a result of environmental conditions, of geometry, and cross-sections. I hope you all enjoyed watching this very informative video, and we will see you next time in Physics 4.